Welcome to iLecture Online, and here's a nice little example of how to find the angular acceleration of a real object that has moment of inertia. And the way we approach that, let's take a quick look at our example here. We have a wheel here, and they're asking you to find the angular acceleration of the wheel. The wheel has mass, it has a radius, and we're applying a force tangential to the surface of the wheel. So first of all, we understand that since it's an object that can rotate, it has moment of inertia. So I, in this case, will be mr squared, because it looks like all the mass is distributed at the very end of the radius of the object. The spokes can be assumed to be very, very light and do not play a role in this. All right. Then we also see that the force is applied tangentially, so that means that there's a torque applied to this. The torque, by definition, is force times the perpendicular distance from the line of action to the force to the point of rotation. So this here would be the perpendicular distance. Here's the line of action of the force, like this. And this is the perpendicular distance from that line of action of force to the point of rotation, which is this right here. Now, knowing the moment of inertia and knowing the torque, we can now find the angular acceleration. Remember Newton's second law that says F equals ma? Well, that famous equation, one of the most known equations in physics, can also be expressed in terms of angular motion. This is, of course, for linear motion, but for angular motion, we replace the force by the torque, and replace the mass by the moment of inertia, and replace the angular acceleration by, the linear acceleration by angular acceleration. So F equals ma can be expressed in terms of rotational motion as well, and then it becomes the torque equals the moment of inertia times the angular acceleration. And again, if we think of a rotating object that has radius r, and it has an angular acceleration alpha, then what is the tangential acceleration? And of course, a tangential will be equal to r times angular acceleration. Or the angular acceleration can be expressed as the tangential acceleration divided by r. So if we want to know the angular acceleration of the wheel, we can solve for alpha. If you want to know the tangential acceleration of the wheel, then we have to make this replacement right here. But since they're only asking us to find the angular acceleration, we can say that alpha is equal to the torque divided by the moment of inertia. And the torque in this case is the force times the perpendicular distance from the line of action of force to the point of rotation divided by the moment of inertia, which is mr squared. Now plugging in all those things, well, first of all, the distance right here is the radius of the wheel, so that's f times the radius divided by mr squared. So this r cancels out that r, and finally we have f divided by mr. The force applied tangentially is 20 newtons. The mass of the wheel is 4 kilograms. And the radius is 25 centimeters, which is 1/4 of a meter, 0.25 meters. And you can see that 4 times 0.25 is 1, and that means that we have an angular acceleration of 20 radians per second squared, and that will be the angular acceleration. If you want to find the tangential acceleration, then we go here and we say, okay, that means that the tangential acceleration is alpha times r, which is equal to 20 radians per second square times the radius of this, which is 0.25 meters. So that would be 5 meters per second square. Remember that radians is not a unit. It's just there for convenience, for clarity. And so you can find the angular acceleration or the tangential acceleration using what I would call the rotational equivalence of Newton's second law. And that's how you do this problem. Now, the next example, we'll use a pulley, and we'll have to try and find out what the acceleration of a pulley is when we consider that the pulley itself has mass and therefore a moment of inertia. So that's a little bit more tricky. So let's see how the next one is done.